And so once we got that far, we thought we were starting to understand that bacteria have these social behaviors, but what we were really thinking about is that most of the time bacteria don't live by themselves. They live in incredible mixtures with hundreds or thousands of other species of bacteria. And that's depicted on this slide. This is your skin. So this is just a picture, a micrograph of your skin anywhere on your body. It looks pretty much like this. And what I hope you can see is that there's all kinds of bacteria there. And so we started to think, if this really is about communication in bacteria, and it's about counting your neighbors, it's not enough to be able to only talk within your species. There has to be a way to take a census of the rest of the bacteria in the population. So we went back to molecular biology and started studying different bacteria. And what we found now is that, in fact, bacteria are multilingual. So they all have a species-specific system. They have a molecule that says me. But then running in parallel to that is a second system that we've discovered that's generic. So they have a second enzyme that makes a second signal, and it has its own receptor, and this molecule is the trade language of bacteria. It's used by all different bacteria, and it's the language of interspecies communication. And so what happens is that bacteria are able to count how many of me and how many of you, and they take that information inside and they decide what tasks to carry out depending on who's in the minority and who's in the majority of any given population. And so then again, we turned to chemistry, and we figured out what this generic molecule is. So that was the pink ovals on my last slide. This is it. It's a very small 5-carbon molecule. And what the important thing is that we learned is that every bacterium has exactly the same enzyme and makes exactly the same molecule. So they're all using this molecule for interspecies communication. So this is the bacterial Esperanto. And so once we got that far, we've started to learn that bacteria can talk to each other with this chemical language. But what we started to think is that maybe there's something practical that we can do here as well. So I've told you that bacteria do have all these social behaviors that they communicate with these molecules. And of course, I've also told you that one of the important things they do is to initiate pathogenicity using quorum sensing. So we thought, what if we made these bacteria so they can't talk or they can't hear? Couldn't these be new kinds of antibiotics? And of course, you've just heard and you already know that we're running out of antibiotics. Bacteria are incredibly multi-drug resistant right now, and that's because all of the antibiotics that we use kill bacteria. So they either pop the bacterial membrane, they make the bacterium so it can't replicate its DNA. We kill bacteria with traditional antibiotics, and that selects for resistant mutants. And so now, of course, we have this global problem in infectious diseases. So we thought, well, what if we could sort of do behavior modifications? Just make these bacteria so they can't talk, they can't count, and they don't know to launch virulence. And so that's exactly what we've done, and we've sort of taken two strategies. The first one is we've targeted the intra-species communication system. So we've made molecules that look kind of like the real molecules, which you saw, but they're a little bit different. And so they lock into those receptors and they jam recognition of the real thing. And so by targeting the red system, what we are able to do is to make species-specific or disease-specific anti-quorum sensing molecules. We've also done the same thing with the pink system. We've taken that universal molecule and turned it around a little bit so that we've made antagonists of the interspecies communication system. And these, the hope is that these will be used as broad-spectrum antibiotics that work against all bacteria. And so to finish, I'll just show you the strategy. And this one, I'm just using the interspecies molecule, but the logic is exactly the same. So what you know is that when that bacterium gets into the animal, in this case, a mouse, it doesn't initiate virulence right away. It gets in, it starts growing, it starts secreting its quorum-sensing molecules. It recognizes when it has enough bacteria that now they're going to launch their attack and the animal dies. And so what we've been able to do is to give these virulent infections, but we give them in conjunction with our anti-quorum-sensing molecules. So these are molecules that look kind of like the real thing, but they're a little bit different, which I've depicted on this slide. And what we now know is that if we treat the animal with a pathogenic bacterium, a multi-drug resistant pathogenic bacterium, in the same time we give our anti-quorum sensing molecule, in fact, the animal lives. And so we think that this is the next generation of antibiotics, and it's going to get us around, at least initially, this big problem of resistance. So what I hope you think is that bacteria can talk to each other. They use chemicals as their words. They have an incredibly complicated chemical lexicon that we're just now starting to learn about. And of course, what that allows bacteria to do is to be multicellular, right? And so in the spirit of TED, they are doing things together because it makes a difference, right? So what happens is that bacteria have these collective behaviors, and they can carry out tasks that they could never accomplish if they simply acted as individuals. And what I would hope that I could further argue to you is that this is the invention of multicellularity. Bacteria have been on the Earth for billions of years, humans, a couple 100,000. So we think bacteria made the rules for how multicellular organization works, and we think by studying bacteria, we're going to be able to have insight about multicellularity in the human body. So we know that the principles and the rules, if we can figure them out in these sort of primitive organisms, the hope is that they will be applied to other human diseases and human behaviors as well. I hope that what you've learned is that bacteria can distinguish self from other. So by using these two molecules, they can say me and they can say you. And again, of course, that's what we do both as in a molecular way and then also in an outward way. But I think about the molecular stuff. This is exactly what happens in your body. It's not like your heart cells and your kidney cells get all mixed up every day. And that's because there's all of this chemistry going on, these molecules that say who each of these groups of cells is and what their tasks should be. And so again, we think that bacteria invented that, and then you've just evolved a few more bells and whistles, but all of the ideas are in these simple systems that we can study. And then the final thing is, again, just to reiterate that there's this practical part, and so we've made these anti-quorum sensing molecules that are being developed as new kinds of therapeutics, but then to finish with a plug for all the good and miraculous bacteria that live on the Earth, we've also made pro-quorum sensing molecules. So we've targeted those systems to make the molecules work better. And so remember, you have these 10 times or more bacterial cells in you or on you, keeping you healthy. What we're also trying to do is to beef up the conversation of the bacteria that live as mutualists with you in the hopes of making you more healthy, making those conversations better so bacteria can do things that we want them to do better than they would be on their own. And then finally, I wanted to show you, this is my gang at Princeton, New Jersey. Everything I told you about was discovered by someone in that picture. And I hope when you learn things like about how the natural world works, I just want to say that whenever you read something in the newspaper, you get to hear some talk about something ridiculous in the natural world, it was done by a child. So science is done by that demographic. All of those people are between 20 and 30 years old, and they are the engine that drives scientific discovery in this country. And it's a really lucky demographic to work with. I keep getting older and older, and they're always the same age, and it's just a crazy, delightful job. And I want to thank you for inviting me here. It's a big treat for me to get to come to this conference.